Hello, welcome back. Today we're going to take a look at series. Now, in my previous video, we talked about whether or not a sequence converges or diverges. In this video, we're going to take a look at if a series converges or diverges. Now, to remind ourselves, a series is the sum of terms of a sequence. So when we take a look at the notation down here, this is what we call an infinite series or an infinite sum. Our sequence is denoted as this a sub n, and we're going to let n go from 1 to infinity. And what we want to find out is if we have a sequence and we add up all the terms of that sequence, we want to know if that sequence, the series, will converge or diverge. Now, so let's take a look at a couple different sequences here. Let's let a sub n equal 1 over n, and let's let a sub n equal just n. Now, let's list out the first five terms. The first one is going to give me 1, 1 half, 1 third, 1 fourth, 1 fifth. If you notice, these values are going to get smaller. That's a good thing. If we want something to converge, that limit has to approach zero. And that's what we talked about in our previous video for sequences. If we let n go to infinity here, we get zero. And for a series to converge, we're basically saying we want to make sure that if we want this to converge, that that last term has to be quote unquote zero per se. That's different if we looked at a sub n. If we look at the first five terms here, 1, 2, 3, 4, 5, clearly these values are getting larger. And if we try to take the limit, if we try basically to find the last term, we get infinity. So we know that this will diverge. In other words, it's never going to approach a value, so that will not converge. So the first thing we have to always make sure is that the limit as n goes to infinity has to approach zero. The terms of the sequence must approach zero. This is a must. We do not want a diverging uh, series here or sequence. Now, so let's get back to our example. So if we want to find out if a sequence converges, what we're going to do is we're going to look at area. So, because a series is a list of finite terms, n goes 1, n is 2, n is 3, we have to use a Riemann sum. It's not infinite number of terms like an integral, so we're going to use a Riemann sum here. And let's take a look at the area under a curve. Now, so we're going to let the x-axis be the n, the term number, and we'll let the y-axis be a sub n, the value of that sequence at that time, at that place. So if we let n be 1, n be 2, n be 3, n be 4, and n be 5. So what we want to do is we want to find the values of these terms. And we can find the values of these terms by plugging them into our sequence. If we let a be 1, we would get a sub 1 way up here. We would wind up here. Now remember, it has to be a decreasing value. So a sub 2 will have to be lower than a sub 1. So we'll make it right here maybe. A sub 3, again, it has to be decreasing. A sub 4, a sub 5, and so on and so forth. Now, since it's a Riemann sum, we are going to use rectangles. So I'm going to do a left-hand Riemann sum. So between 0 and 1, I'll use the value of 1. Ready? A sub 2, there it is. A sub 3, there's that area. And 4, there's that area, and there's that area. Now remember, this continues on forever. So if I wanted to find the area underneath this, so I want to know what happens to the area. Will that area converge or diverge? Because in order to find out if my series will converge, I just want to take a look. Will that total area converge here? And if I take the area here, my first rectangle, these all have a width of 1, every single one of them. And their heights, well, that's just the height of my first rectangle. It is a sub 1 by 1, or a sub 1, plus my second rectangle, also 1, but this time it has a height of a sub 2. So we get a sub 2. And if I continue that pattern, this is 1, a sub 3. So I get plus a sub 3, and it keeps going. Now, if you notice, this is a definition of a series that you did last year in pre-cal. So we haven't changed anything. So looking at the area using Riemann sum just generates our series like you did last year in pre-cal. But remember, because this is an infinite series, we want to go on forever. So we want to find out what happens as this thing goes on forever right here. So we unfortunately though we can't add an infinite number of terms. So this doesn't work out too well for us if we tried it. So since so the question is, well, how can I find out this? Well, rather than looking at a Riemann, one way I can do it to approximate my area is I can use an integral. So what I can do is I'm going to connect these dots right here. I'm going to connect these like so. If I connect all those little points right there. And what I'm going to do is I'm going to call this function here in red, this function here, f of x. Now notice f of x at the integral part is the same values right here. But what I'm going to do is I can find the area underneath f of x. So to get the area of f of x, that is just the integral, and it's going to start from 1 and go to infinity. And this is going to give us f of x dx. Now, one thing you should notice, now note I did do a left-hand Riemann sum, and you can prove this also with a right Riemann sum too, is if I'm looking at the area from 1 to infinity here, notice the area of this rectangle actually covers more region than my Riemann sums. We learned when we did Riemann sums, they're not the most accurate because they always have this little tiny errors right up in there. But my integral covers those areas as well. So what I'm going to do instead is I'm going to solve this integral itself. And this is what happens. Now, be careful though. Notice this is improper, so we would have to write this as a limit as b goes to infinity from 1 to infinity, 1 to b, excuse me, of f of x dx. So what we're going to do now is we're going to solve this integral. And here's the thing. Um, if the integral converges, so what we can say then, if the integral converges, now take a look at the picture again. If the integral converges, notice, remember, the integral covers more area. Then the Riemann sum is also going to converge because it has less area underneath it. So we say if the integral converges, therefore we say the summation will also converge. Likewise, what happens if the integral diverges? Well, let's think about this. So let's think about if the integral diverges. Well, if the integral goes on forever, if the area of the integral seems to grow forever, that means I'm always adding more rectangles as well. I can add more rectangles, so therefore we can say that s- the series will also diverge. I tend to think of this is what we call the integral test. And what I tend to think of it as, hey, think of it as like a car. You're following a car. Uh, you are like the series. You're the series. And if the car in front of you stops, you stop. You converge. If the car in front of you keeps going, you just keep going. So if the car in front of you diverges, drives to infinity, you're going to drive to infinity. So let's take a look at just a real quick example here. Here we have the series 1 over n, like we saw before. One, we already know that this is going to have a limit approaching 0. So if we were to graph this out, looking at area, we would get 1, let n be 1, 2, 3, 4. My height at 1 is just 1 here. My height here, without having a height of 1, would be 1/2, 1/3, and 1/4. So I want to find this area. Well, my area would just be my terms, 1 plus 1/2 plus 1/3 plus 1/4, and it keeps going. Unfortunately, it goes on forever, and we really can't determine what that value is actually going to be. So instead, I'm going to write an integral instead. Now we're using a left-hand sum again, and there's a reason for that. We'll talk about that in another video. We'll see why we do that. So now what I'm going to do instead is, well, I'm going to say a few short words. One, I have to recognize that this is a decreasing function. So I could say, I am going to redefine my function as f of x equals 1 over x. And this is, and we're going to say a few short words that this is a continuous function. We have to say that's continuous. Continuous. And it is always going to be positive, so the values will never be negative, so it's not going to alter anything like that. And it is a decreasing function. In other words, we said that the limit approaches 0 there. Once we have that, we can now solve an integral 1 over x from 1 to infinity. We start at 1 because that's where the problem starts. This is improper, so we're going to write this as a limit as b goes to infinity of 1 to b. Now, this is a really easy one to solve. This just gives us the natural log of x from 1 to b. And solving it, we get the limit as b goes to infinity. We get the natural log of b minus the natural log of 1, which we already know is 0. And if we let b go to infinity, this goes to infinity. Therefore, we say that this diverges. So we're saying here that the area of my integral diverges. It goes on forever and ever and ever. And remember, what that means is if my area keeps going on forever, that means I can always add more rectangles for my Riemann sum. Remember, Riemann is going to give me my series. But because my area grows forever, and we already know that my area above here, my area incorporates more area than my Riemann sum, if that's going to diverge, and I can always add more rectangles, then my series will also diverge as well. So we would say, therefore, the series, and we say the following, diverges, whoops, by what we call the integral test. So what we know is that this sum, even though the values are getting smaller and smaller and smaller, the actual values grow to infinity. The sum itself grows to infinity. All right. I hope you enjoyed this video. I will see you in my next one. Bye bye.